We discuss another element of general linear model. It is called Ancova. Ancova goes for analysis of covariance. However, the code word here is rather not a covariance but a covariate. Covariate is a variable that influenced or which we know that is in the relation or linear relation with our dependent variable, but which is not controlled in the experiment. It, however, can be measured and considered while analyzing the outcome of the experiment. Ancova can be viewed either as a variant of ANOVA with the additional covariate element or as a variant of multiple linear regression. The discussion will consist of 3 parts, each one in separate short film. The first will be about presenting the idea of Ancova, illustrated with some artificial data. The data are chosen in such a way that they fit this method ideally. In real life data, usually things are not that clear. So the second example will be about real life data on the same subject, but as usual, a little bit messier. And the third part will be another example with more complicated statistical setting. So let us start with presenting Ancova with our artificial example. So the example is about assessing the value of new learning method. We performed an experiment on a group of students. Students are supposed to prepare for an exam, and the whole group of students, there were 78 of them, is divided into 2 groups, a control group and experimental group. The control group is supposed to study for the exam in their usual way, and the control group is asked to use the new method. After the exam, the scores of students are gathered and analyzed. And what is important here, we know that it is not only the way we study for the exam that influences the result, but also the individual skill of each student. Regardless of the method of study, definitely the result of the exam depends on the individual skills. So how we can take this into account? We can construct a variable that somehow measures this, and in our case the variable that measures individual skill of students will be based on their performance in class. For example, if students gather some point during the whole semester, then the number of points can be used as a covariate. The assumption is that a covariate is related linearly with the dependent variable. So in our example, we have the dependent variable, which is the result of the final test. There is the covariate, individual skill based on the performance in class, and there is the experimental variable, which takes value 0 and 1, 0 for the traditional method of studying and 1 for the new method of studying. Here we have some information about the data itself. The histogram of the results of exam in the group studying in normal way, histogram in the group studying using the new method, and the histogram in the whole group of composed group of students. And to investigate linear dependence between a covariate and the dependent variable, we look at the scatter plots. First, separately, we can see two things. First, that there is definitely linear dependence between the covariate and the dependent variable. So the name covariate is justified. However, those scatter plots are suspiciously similar, and this is because these are artificial data. When we put both scatter plots on one picture, we see that in the general, this linear dependence is still here. However, the red dots that refer to the control group and blue dots that refer to red dots are referred to the experimental group and blue dots refer to the control group, are a little bit translated with respect to each other. So just looking at the picture, we see that probably the experimental group did a little bit better during the exam. What is important for Ancova is that there should be no interaction between the covariate and the experimental variable. The interaction can be investigated by looking at regressions, linear regressions in groups. Here we have a picture, the same scatter plot with superimposed linear regressions. The red one again is the experimental group and the blue one is the control group. And we see that the regression lines are almost parallel, which means that there is no interaction between the covariate and the experimental variable. Now, in real life data, usually this is not that elegant. And if it happens, if there is a significant interaction, we can either introduce additional variable that takes the interaction into account, or we can just forget the whole method. We are going to compare Ancova with ANOVA. Therefore, let us start with usual ANOVA, and everything here is calculated by hand. However, as you can see, we use sorry for that. Oh, okay. We use linear regression methods. So instead of separately calculating group means, I have just fitted a linear regression to the pair of variables, the dependent variable and the experimental variable. However, since the experimental variable takes values only 1 and 0, the numerical results will be the same. So if I just take value of the regression for variable number 3 equal to 0 and value of the regression with variable 3 equal to 1, then I get just the means that I need in ANOVA. So here I see that there is a difference. Almost 5 points, 3.7 points between exam results in the control group and exam results in the experimental group. And experimental group did a little bit better. However, when we look at squared correlation coefficient, we see that this dependence is not that big. Only 6% of the total variance of the dependent variable is explained by the relation with independent variable, the experimental one. Therefore, it is definitely not a strong dependence. And the p-value is quite large. If we assume the significance level 0.005, then we state that the difference is not significant here. Before we do the calculations for Ancova, let us discuss how how the whole test is constructed. So what we do in Ancova, we in fact compare two linear regressions. One is the so-called reduced model that consists of linear regression of the dependent variable with respect to the covariate. And the second is the so-called full model with both the covariate and the experimental variable here. In each case, for both regressions, we calculate sum of squares of errors, which as usual measure how well the model fits the data. And in our case here, we use not in our case, but in general, the full model gives sum of squares of errors which is not bigger than the sum of squares of errors of the reduced model. This is because when we add the information to the regression, we can only make things better. If this information is not valuable, then this sum of squares of error is only a little or not at all less than the previous one, but we cannot increase the error adding new variable. If we want to measure how valuable the information given by experimental variable is, we can take the difference of sum of squares of errors and compare it to something, because the sum of squares of errors is a relative, those numbers are relative, of course. So we have to compare them to something. And as usual in constructing f-type variable, we compare it to the full sum of squares of errors, so the model sum of squares of errors. And we have to take into account the degrees of freedom. In the denominator, there is the usual formula number of elements in the sample minus number of parameters that were determined, and we have three parameters: the intercept and two slopes, and the number of degrees of freedom of the enumerator is the difference of the number of degrees of freedom of the two of them. This has number of degrees of freedom n minus 2. This has number of degrees of freedom n minus 3. So at the end we have 1 degree of freedom in the enumerator. Note that this formula is very similar to the formula for the squared partial correlation coefficient. The only difference is what we compare this difference to. Defining f, we compare the difference with we compare the difference to the model sum of squares, and calculating rho square, we compare the difference to the reduced, so this initial sum of squares that we get without adding additional information. The f variable can be also expressed in terms of correlation coefficients. Of course, the formula that I'm going to derive now is valid only for such a case when we have dependent variable, one covariate, and one experimental variable. So we start with our definition. The differences between sum of squares of errors and the degrees of freedom. And then we recall the definition of the partial correlation coefficient that we mentioned already before. And from this definition, we can express the enumerator using the correlation coefficient multiplied, there is some information lacking here. This should be multiplied by sum of squares of errors of the reduced model. It should be here. Similarly, we can look at the definition of the squared correlation coefficient for multiple linear regression, and from that we can express this time the denominator using sum of squares of errors of the model. The sum of squares of error of the model can be expressed by the total sum of squares, which is variance multiplied by the number of subjects and squared correlation coefficients. And when we put all those things into the formula, we get the following formula with some correlation coefficients here. Next thing we can do, we can get rid of this sum of squares using again the same trick as we used here. So use the definition of the regression of the correlation coefficient calculated from regression, and this will depend on the total sum of squares, which at the very end will cancel. So at the very end we arrive at the formula that gives us f that depends on excuse me, that depends on the partial correlation coefficient, and which is rescaled a little bit by some number based on correlation coefficients for the full model and for the reduced model. Okay, so we can use the formula if we want to calculate things by hand. We can do it. And this is what I did here. I used exactly the formula that I derived. And we have the results as follows. First, let us look at correlation coefficients. So this is the correlation between dependent variable and covariate, and it is quite large. We have seen that the dependence was strong. Those experimental points really lie almost on a line. When we add information about the method of studying, R squared increases. We expected that it increased, but it seems that it increases substantially enough. This partial correlation coefficient that says how strong is the dependence between between the dependent variable and the experimental variable when we control the influence of the covariate is 0.36. So it is also significantly larger than the appropriate coefficient in case when we didn't control the covariate, and we calculate the p-value, which in this case is very small, 10 to the number of 10 to the minus 11, to the power of minus 11. So this is very small. Therefore, the difference that we observe here, we consider it the difference between the performance of students that use new method and the performance of students that used old method. We consider this performance significant. Okay, so that's all for now. I stop the recording, and the next recording will be about analyzing real life data about the same subject, the same problem.